Hello again, everybody, and welcome back. This is a continuation of example 5. I believe it is 5.8, and this is part B of example 5.8. Now, what I went ahead and did is I redrew the example. If you recall, there was the two boys pushing on the block of ice, and we did part A and found out the acceleration of the block. With part B, we're asked to find the normal force exerted on it by the table. So, in this example, not until now have we really even addressed the idea of the normal force. What we're being asked to find is, what kind of force is being exerted upwards by the table? And I'm going to draw this in black so that it stands out a little bit. But we've got a bunch of forces acting downwards. We've got the y force from force 1, the y component of force 1. Force 1y is 11.3 newtons down. Force 2y is 5.5 newtons down. You've got the weight force, mg, right here. The table has to support all this, so the table must create a normal force upwards to support all this funny business going on up above. Okay? So, again, I just redrew all this from the previous problem. All these values, f1x, f1y, f2x, f2y, we already calculated in the last section. We want to find out what the normal force is that the table has to supply. All right, now our assumption is going to be, since we're dealing with the y direction, we're going to call the up direction positive and the down direction negative. So when we write our net force statements, we'll take that into account. Okay, so let's write our global statement about the net force. And in this case, I'm going to write it in blue. In this case, the net force that we care about is in the y, or the direction we should say we care about is in the y direction, right? The net force in the y direction equals mass times acceleration in the y direction. Well, like I said in the previous segment, how is the box, or the block of ice, how is it accelerating in the y direction? The answer is it's not. It's not flying up off the table. It's not sinking down into the table. It's not breaking the table. So that, being 0, is going to cause the whole net force in the y direction to be 0. 0 newtons. So what must be true is that the downward weight force and the downward y component of this force and the downward y component of this force must be balanced out, must be counteracted by this upward normal force supplied by the table. And by the way, we're going to write that in equation form right now, because the other way we can write the net force in the y direction is as being the sum of all the forces. So we're going to call up positive and downwards negative. So I'm going to write my normal force first, right? Normal force is up and it's positive. So normal force plus, or I should say, I'm sorry, normal force minus what? All these other downward acting forces. F1y minus F1 in the y direction minus F2 in the y direction. Also minus what else? Minus the weight force of, or that is not minus, but it's counteracted downwards by the weight force of the block itself, mg right there. Both of these statements being true or equal to each other, describing the same thing, we can set them equal to each other, so we can solve for that the normal force. So we're going to write this equal to this, which is really equal to 0, right? So the normal force is going to be equal to, normal force minus, I'm going to stay with black here, F1y minus F2y minus mg equals 0. Well, it doesn't take too many algebra skills to know what to do with this to solve for the normal force. We're going to add this, and add this to the other side so they all become positive. So the normal force, the force that the table has to supply, is going to be F1y plus F2y plus mg. it's got to be equal to and balancing this downward force, this blue downward force, and this downward force as well. All right, so what is that? What are those values? F1y, that's 11.3 newtons. F2y, that's 5.5 newtons. And mg, that's going to be, what's the mass of the block? I believe that is 6 kilograms. All right, back here. Yep, 6. Haven't been back there for a while. 6.0 kilograms times 9.81 meters per second squared. This is going to give us our normal force, the force that the table has to supply in order to counteract all those downward forces. So 6 times 9.81 plus 11.3 plus 5.5, I get 75.7 newtons. That's counteracting all those forces, the downward weight force, the downward push from this boy, the downward push from this boy as well. The normal force is acting up from the table, supporting all those, preventing any kind of motion in the y direction, having the y, the net force in the y direction, be 0. Okay, so that's our first problem, dealing with normal forces, and we just calculated that by summing our normal forces being equal and opposite to all the other forces being acting downwards. So that's it for this problem, for part B of example 5, 8, I believe. And if you have any questions, please come see me. But in the meantime, thanks for following along. I'll see you on the next one.